This is a problem from the book, Introduction to Quantum Mechanics by David Griffiths. Problem 1.9, a particle of mass m is in the following state. Part A, find A. We're going to make use of the normalization equation. Part B. For what potential energy function V of x does psi satisfy the Schrödinger equation? Part C. Calculate the expectation value of x, x squared, p, and p squared. And Part D. Find the standard deviation in position, sigma sub x, and the standard deviation in momentum, sigma sub p. Is their product consistent with the uncertainty principle? For this part, we normalize the wave function to find A. This is the complex conjugate of the wave function. A is assumed to be real. Then we substitute psi and psi conjugate into the normalization equation. This is a Gaussian integral, and the equivalent is in the form, square root of the quantity pi over k, where k is equal to 2am over h bar. Then applying some algebra, we get the value of A. This is the time-dependent Schrödinger equation. Using the equivalent of psi, we can find the partial derivative of psi with respect to t, and the second partial derivative of psi with respect to x. So taking the first derivative of psi, we have but this is just the equivalent of psi. So the first derivative of psi is simply negative ai psi. Now let's take the second derivative of psi with respect to x. Factoring out negative 2am x over h bar, we get the equivalent of psi. Now, let's differentiate it once more. Here, we used the product rule. This is simply negative 2am x over h bar, times psi. After simplification, we get. Now we can plug these values into the Schrödinger equation. After some simplification, we get our potential energy, which is 2a squared mx squared. This is the equation for finding the expectation value. Inserting the value of psi and psi conjugate. Simplifying the integrand, we get. This is an odd function and is to be integrated over a symmetric interval. So the result for the expectation value of the position x is 0. Using the same formula, we can find the expectation value of x squared. This is a Gaussian integral of the form, integral from negative infinity to positive infinity of x squared times e, raised to negative kx squared dx. And the answer for this integral is square root of pi over 2 times the square root of k cubed. Here, k is equal to negative 2am over h bar. So now our expectation value for x squared is given by, which can be simplified to h bar over 4am. Now for the expectation value of the momentum p, we insert the momentum operator. We already know from the previous part, that the first partial derivative of psi with respect to x is negative 2amx over h bar times psi. Now this is nothing but the expectation value of x, which, from our earlier calculation, is equal to 0. Therefore the expectation value of p is 0. Now for the expectation value of p squared. We already know the equivalent of the second derivative of psi from earlier. So we can insert it into this equation. Evaluating the integral and simplifying, we get amh bar as our answer. Now we're going to use the results from part C to solve for the deviation of position and momentum. Sigma sub x is given by this equation. Inserting the expectation value of x squared and the square of the expectation value of x, then taking the square root, we get the deviation in position. Same can be done for the deviation in momentum. Now, according to the uncertainty principle, the product of this two has to be equal or greater than h bar over 2. In this problem, we see that the product is h bar over 2. Therefore the uncertainty principle holds. Here's a summary of our solution for this problem. And the list of equations used in solving this problem. Hope this helps. Thank you for watching.